Section 11.5, video 2. So the second half of this section is on estimating sums, just like we've looked at in the last couple of sections. All right, so remember, a sum of a series is the limit of the partial sums. And as a reminder, a partial sum, typically written S sub n, is the sum of the first n terms of the series. So a partial sum, Sn, of any convergent series can be used as an approximation. This is because the limit of the partial sums is the sum itself. But unless we know how far off we're going to be or how bad of a guess that partial sum is, it's not much use, is what is being said here. So just like in the past couple of sections, we want to introduce the idea of error or a remainder. So here we say that the remainder, Rn, is S minus Sn. And notice this is the same definition as you've seen before. S is the actual sum of the series, and S sub n is the partial sum that you used to estimate. So the remainder associated with that estimation is simply the difference of your guess and the true answer. So what's our theorem for estimation? If S is the true sum of an alternating series that you know is decreasing, which is condition 1, and the limit is 0, so that you know that it converges, then the absolute value of the remainder is the absolute value, which is the absolute value of the difference of S and Sn, is less than or equal to B sub n plus 1. So this is kind of powerful because it says that your remainder or your error is always going to be less than or equal to whatever the next term was. And that's what this previous slide was trying to say. It says the next theorem says that for series that satisfy the conditions of the alternating series test, the size of the error is smaller than the absolute value of the first neglected term, the first term not used in the partial sum. So if we used Sn to estimate our sum, then the very next term, the very next positive term, Bn plus 1, is going to be your upper bound for error. So how can we use this in an example? Find the sum of the alternating series where, let's see, what do we have? Negative 1 to the n means our first term is negative, and then Bn would be 1 over n factorial. Remember, n exclamation mark, that's a factorial, and it means the product of that number and every integer less than it. So 3 factorial is 3 times 2 times 1, and so on. So the question says, find the sum correct of 3 decimal places. So before we do that, we should probably make sure that there is a sum, or rather that it's convergent. So we need to decide if we can use the alternating series test. The first question is the positive version of the terms decreasing? So the n plus 1 term would be 1 over n plus 1 factorial. How does that compare to 1 over n factorial? Well, n plus 1 factorial is bigger than n factorial. So if you divide it into a fraction, 1 over n plus 1 factorial, it's going to be less than 1 over n factorial because this bottom is bigger. It's a smaller fraction than this one. So it does satisfy the first condition. The second condition is the limit has to be 0. So what's the limit of 1 over n factorial? Well, as you can imagine, n factorial grows incredibly quickly. So as n goes to infinity, 1 over n factorial absolutely goes towards 0. In fact, much quicker than 1 over n, which is what they're using to compare to here. So definitely this converges to 0. So since both of these are true, we definitely know that this series is convergent. So now we can focus on what they're actually asking to find the sum correct to 3 decimal places. Okay, so because we don't have an exact science for this at this point, let's write out some of the terms and see if we can get any ideas. So they wrote out the first, 1, 2, 3, 4, 5, 6, 7, 8 terms of the series, which is the 8th partial sum if you ignore the dot, dot, dot. So we have 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, and so on. So remember, or I don't think I've ever told you this, but 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6, 4 factorial, 4 times 3 times 2 times 1, which is 24, and so on. You can also just use the previous factorial and multiply by the new number. For example, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So 6 times 4 gets us to 24. 24 times 5 gets us to 120. 120 times 6 is 720, and 720 times 7 is 5,040. So basically what we've written out here are the first 8 terms of the series so that we can understand what do these terms look like. Okay, so something to notice, the 7th term, ignoring the sign, of the series is 1 over 5,040. This is from the last one from the previous slide, ignoring the sign. That is about 0.0002. And the partial sum, S6, using the n right before it, because remember we want to compare n and n plus 1, S6 would be the sum of the terms up until B7. That is about 0.368056. So using the estimation theorem, we know that the remainder, the error, I should say, of using the 6th partial sum would be less than or equal to B7, the next term, which we just found is about 0.0002. So this error of less than 0.002 does not affect the 3rd decimal place. Well, what does that mean? The 3rd decimal place is this 3rd zero, which is the thousandths place, right? So definitely subtracting or adding 0.0002 is not going to affect the 3rd place because it's so much smaller than that 3rd place. So what we're saying here is that this error is sufficiently small to satisfy the original question of getting an answer that is correct to 3 decimal places. So we can use S6, which was about 0.368, to say that we know this value is correct to 3 decimal places, because the worst the error is going to be is 0.0002. So whether or not we subtract that or add that to here, we're still going to be right within 3 decimal places. So going 7 terms in, or 6 terms, whichever way you want to look at it, is good enough in this case to find a sum correct to the thousandths place. Okay, and lastly, just want to mention that the pattern of the partial sum, or the error using a partial sum being smaller than the next neglected term, is really only something that works for alternating series specifically. So make sure you don't accidentally try to use this idea for a non-alternating series.